So up to this point, we've been talking about energy. And one of the key parts about energy is that the system energy is conserved. We're always going to just be trading that kind of energy back and forth. You know, if I have something getting launched up, I'm trading its kinetic energy for gravitational potential energy. If I have something coming back down, well, I'm trading its gravitational potential energy for kinetic energy. Same thing goes true for elastic potential energy and any other kind of energy you can think of. However, what if I don't want to consider just the whole system? What if I want to talk about one specific object? Well, at that point, we definitely cannot say that the energy is conserved, right? Because the velocity, for example, of that object, that robot, could change. And if it does, well, then its energy has changed. Where did that energy go? Seems to be lost. Okay, it's actually out in the system somewhere. But if I'm only looking at one robot, if I'm defining my system to be that one robot, it's going to look like energy is violated. So what we need is another approach for when we can describe what's happening to a single robot. And the way we do that is to focus on the momentum of that robot and what can cause the momentum of that robot to change, even if I'm looking at it by itself. Let's get started. All right, so to get started, let's think about the situation we've been dealing with up to this point. Let's say I've got two robots and they collide. And just to keep things simple, let's assume that they're moving at the same velocity, but of course, if they're going to collide, they have to be in opposite directions. So I've got these two robots that are coming at exactly the same speed, so the magnitude of their velocity is the same, but the direction is opposite. Look at microtask 1 then. What is the total momentum of the system before the collision? Stop and think about that. Well, remember, momentum's a vector. So if I have some momentum going this way and the same amount of momentum, the same magnitude of momentum going this way, the total momentum of the system then is going to be 0. Well, based on this, what's going to be the total momentum of the system after the collision? The momentum's conserved for the whole system, so that's going to be 0. So that's pretty straightforward. That's what we've been working with all this point. But what if I only want to look at one of the robots? So if I have this robot and it collides with something, whatever, then its momentum is going to change. And that seems to be magic, right? Because that momentum is coming from somewhere. We don't know where. So this problem was first addressed by Isaac Newton in around 1687 or so. He wrote this book called The Principia. And in that, he laid out his 3 laws for motion. Now I'm going to tell you, you've probably been told about Newton's 3 laws of motion in high school or whatever. There's a good chance you were lied to. So some of the things you were told are simply false with that. For example, just getting ahead just a little bit, but if you think about the Newton's second law, if you've heard of that, you might have heard it phrased as F equals ma. That's not true. Newton never said that. Let's look at the first law. So this is printed down here at the bottom. You may have heard that the first law is an object in motion will remain in motion unless acted upon by an outside force, or an object at rest will stay at rest unless acted upon by an outside force. That is true, but that's also not what Newton said. What he said was an object will change its momentum if and only if it is acted upon by a non-zero net force. So it's not about its motion, it's about its momentum. Okay? So we need to define some terms here. Now, momentum, obviously, we know what that is, but when I talk about the idea of net force, that's going to be the sum of all of the forces. This little Greek letter sigma, that's a capital Greek letter sigma, means sum. So it means take all the forces and add them up. So force, of course, this idea that we're going to define in just a minute, the force is a vector, and that would be, say, you know, this force plus this force plus this force plus, you know, however many forces there are. We're going to add them all up. But remember, we have to vector add them up. All right? So even though, so one thing you can think about it, let's say that we've got a tug of war going on. And so the two teams are pulling, right? Are they applying a force? Oh, absolutely, right? They're pulling very, very hard. But if the team on the left and the team on the right are pulling at exactly the same strength, the same force, then the rope isn't going to move. It's going to stay the same. So it started out at rest. It started out with a velocity of 0, so it's going to remain with a velocity of 0. In other words, its momentum is not going to change. And so that's a case where I have the sum of the forces is actually equal to 0. So this would be, for example, the force of the team on the left plus the force of the team on the right. Now I'm going to write these vectors in terms of magnitudes. So we're going to say they're equal, but they're in the opposite direction. So let's define, here's our people, we're going to look down on them, and one of them is pulling this way, and one of them is pulling this way, right? So let's define, say, this direction to be positive. So the red is the right team is pulling in the positive direction, and the left team is pulling in the negative direction. So that would be like this, and you see that now this is a magnitude because I've taken care of my direction right here. And then my right team is going to be in the positive direction. So again, this is a magnitude. There's my direction. If FL is equal to FR, if the magnitudes of the forces are the same, what is going to be the total force if I add these together? That's going to be 0, right? Because I've got a negative and a positive. So the sum of the forces is 0. That's why it doesn't move. Even though there are forces, it doesn't move because the net force, the sum of all of those forces, is equal to 0. Right? So think about that and make sure that makes sense. Now, this applies even if the robot is moving at a constant velocity. And we're going to deal with this in detail here in just a minute. But if it's moving at a constant velocity, whatever that is, v robot, then is there any acceleration? Is its velocity changing? No. Is its momentum changing? Well, remember that the momentum, which is a vector, and this of course is a vector too, is the mass times the velocity. Well, if the velocity isn't changing, then the momentum can't be changing either. So here is another example of where the net force must actually be equal to 0. So even though the robot is moving, the net force on it is 0 because its velocity, its momentum, isn't changing from that standpoint. All right, so make sure that you understand this. Now, you could put this back into, if we've written it up here, right, where an object at rest will remain at rest. That was our tug of war, for example. It started out at rest. Well, we've got two forces, but there's no net force, so it remains at rest. On the other hand, then an object in motion will remain in motion. Now, it's more precise than that. Not only does it stay in motion, but its velocity does not change. That's because its momentum does not change. So this statement of an object in motion will remain in motion is kind of what we're talking about with our robot right here. But it's not actually correct, because according to that definition, I could actually increase its velocity, couldn't I? And it would still be in motion. But did its momentum change? Yeah. So Newton's law says it will change its momentum only if it's acted upon by a non-zero force. So if that force, let's say, is in the positive direction, right? Let's say that it's positive, and my robot here is moving in the positive direction. Well, then there is a force, which we'll define in a minute, acting in this direction, acting to the right, and so my velocity is going to get higher, just like we see here. So if my velocity is actually changing, I must have a non-zero force, a non-zero net force. Some of all those are. Doesn't mean I don't have forces going in the opposite direction. It just means that they're smaller than the forces that are going in the positive direction. Okay, so turn over to the next page in your book. Newton's second law, you may have heard, remember, was F equals ma. That's not true. And in fact, that only holds for one very, very special case and no other. So in general, this actually isn't true. You've actually been lied to this whole time. So let's look at what Newton said. Newton actually said, let's switch to my pen here, right here. He said that the definition of a force is the time rate of change of momentum. So a force, and we'll use our 3 bars to say it's defined as the change in momentum, let's get that to draw there, in a certain amount of time. So dp, which is our momentum, remember, and that's a vector, dt, that's how we define the force. Now, from an engineer standpoint, that should be the first law. Because remember, we were talking about forces in Newton's first law. Well, wait a minute, you can't use anything until you define it. But, history is what it is. So this then is an example of the definition of the force. Now, this is the instantaneous force, and we're going to talk about this in just a minute. But how would I get, I'm sorry, this is the average force, so this is my average. How would I get the instantaneous force? Well, we've done this before. You just need delta t to go to 0 and take the limit as delta t goes to 0, and then what does it become? It becomes a derivative. So the simple thing is these deltas just become d's. So this is the definition of the instantaneous force. So that's the force at any time. So delta p could actually be changing in time. And we can still take the derivative of it, right? As long as I know how it's changing in time, take the derivative of it, and that's your force. That's how it works. Okay, so let's look at a practical problem then. Now that we've defined what a force is, so we have this situation where, let's say that unfortunately your car has crashed into a brick wall, right? So there's your car, and there's you driving along, right? And you're happy right now, but you're about to not be happy because we're driving into a brick wall. So your car has some sort of velocity, right? And it's got some sort of a mass. Does it have an initial momentum? Sure. What is the momentum? What's the expression for it? Momentum, which is a vector, our initial momentum is going to be m times our initial velocity. Okay, now the question becomes, when this thing hits, your car is going to stop. You're not going to break through the wall, you're not going to pulverize it or anything like that. When you hit, your car is going to come to this terrible, horrible stop right there. And so your final velocity is going to equal 0. So what is your final momentum? Well, that's also 0, right? The mass times 0. So this is going to be 0 kilogram meters per second squared. All right. So that means then that there is a change in momentum. So there is some sort of a force, right? Because we defined if I have a change in the momentum, there must be a net force. There is a net force being applied to your body right now that's making you stop. However, the force doesn't only depend upon the change of momentum. It also depends upon the time over which that change takes place. So you probably know that we have airbags now. So how is it that an airbag actually saves your life? The momentum change is going to happen. You're going to go from whatever momentum you started with to 0. There's nothing you can do to avoid that. How then is it that the airbag is going to make you survive when without it, you're probably toast? Pause the video and think about that. See if you can brainstorm some ideas. Did you think about it? It's really important that you think about these kind of concepts, these conceptual things, because that's your job. Solving problems, well, you're never going to solve any of these problems again. If your boss is just simply not going to hire you to solve a problem that's already been solved from that. So instead, you've got to use these concepts to apply them to new situations. And yes, the situations I'm giving you here are very simple, but that's because we're trying to learn the concepts. All right, so take that time to think about it. So what's happening with the airbag? So with the airbag is extending that collision time. So if you hit with the wall, the collision time might be on the order of, a millisecond. So without an airbag, you're going to hit in a millisecond. And so that change, whatever that velocity is happening over a time. We'll just talk about the average force for now. It's happening over a very short period of time. So what happens to the force? Is it big or is it small if this number is very, very small? Well, if this goes down, then this goes up. They're inversely proportional. So your body is feeling a very, very strong force in that case, right? So the airbag might extend that to, say, 20 milliseconds. I think 23 milliseconds is what we figure here. So what that means then, looking at this is with just colliding with the wall to slow down. Here's the airbag. That means I've got the same momentum change. Can't avoid it. I've got the same momentum change. But now my delta t is much bigger. It's 20 times bigger. And so what that means then is my force is 20 times smaller. So the amount of force, yeah, you might hurt, but you're going to survive because we reduce the force on your body by a factor of 20. That's what that airbag is doing for you. Okay? All right. looking at the next one, then we already talked about our instantaneous velocity or an instantaneous force. But so let's record it here so that we have it. Our force, which remember is a vector, is going to equal dp, which is also a vector, dt. Now this is much more useful, right? Because this then allows me, if I have a momentum that's changing in time, and it is, right? It's not going to just go straight from one velocity to another. There's going to be an acceleration. It's going to be something that's going to change over time. Then I can take the derivative of that, and I can see what the total net force is. We'll be doing that later on in the week. So let's think about it. If you've ever run a robot, then the robot will be moving along, say, at a constant velocity. So let's say that's our velocity of the robot. However, I'm still having to put energy in the system. I'm still having to burn my batteries. As soon as I turn that motor off, does it keep moving at that constant velocity? No, right? So pause the video and see if you can come up with an explanation for why the robot's momentum doesn't change here, right? Because it's got a constant velocity and a constant mass. Why does its momentum not change even though I'm applying a force to it, right? My motors are applying this force. It should be changing my momentum. Why isn't it doing it? Pause the video and think about that. You got some ideas? Well, obviously, if my momentum change, so my change in momentum, if that is 0, so that means that PF is equal to PI, right? If that's 0, then I must have no net force. So the sum of my forces must equal 0, because if I had a momentum change, then I must have a net force. Well, we know we have a force, right? That's the motors. But remember, force is a vector. So my motors, say, are providing a force in this direction. We'll call that Fm. Something must be providing an equal force in this direction. What do you suppose it could be? Well, the most obvious one is friction, right? So it's losing, it's got force. The force of friction is exactly equal to the force of the motors. And so your robot feels no net force, and therefore it doesn't change its momentum. It keeps that constant velocity, right? Okay, take a look at the next page here then. So let's go to our conservation of energy in this situation, and let's see if we can figure out what's going on. So our robot, let's redraw our robot here, right? He's moving on this constant velocity right here. And there is a force going this way due to the motors, and then there's a force going this way due to friction. And remember what a force is. A force is a change in momentum within a certain amount of time. Okay, so pause the video and write down conservation of momentum. So, or conservation of energy. So this force is the force due to the motors, that's an M. The force due to the motors is doing work. It's putting energy into the system. And we've dealt with that before. And we dealt with that last time. We call that WM. That's the work that the motors are doing. How about friction? Friction is doing work as well. Force friction is that, or the work due to the friction. So both of these are energies. So pause the video, see if you can tell me what the conservation of energy would look like. You got it? Make sure that you got it. You really want to work through this. This is what's going to help you. Okay, well, let's think about what we have to start with. So I know that I have my initial kinetic energy, right? And I'm adding in some work done by the motors. And that's going to equal my final kinetic energy. And then I'm losing some work to this. Now remember, there's a number of ways you can do this. And we make a note here. What signs did you choose? If I want to put them both on the same side, I can. I could absolutely say, okay, here's my robot, and I am adding in motor work, and I'm subtracting friction work. And all of those things together is going to give me my final kinetic energy. And of course, if you move your WF to the other side, you're going to get exactly the same thing. It's two different ways of thinking about it. I tend to think of, okay, if I've got any work on this side, it's going into the system, and any work on this side is going out of the system. But as long as you're careful with the signs, that positive means work's coming into the system. That negative means work is going out of the system. And so you can put that all on the left side if you want, if that's the way that makes more sense to you. You do you, and really there's not a wrong way to do that as long as you're careful. Okay. All right. So the change in energy then, I'm going to go ahead and put this, we've run out of space in the box, so let's just write it out here where we can get to it. So my change in energy then, let's copy over what we have first, EKI plus WM, and you can do whichever form you want, they're going to end up being the same. Let's say minus WF equals EKF, since that's the one at the bottom. Okay. Our change in energy then is just EKF minus EKI, right? So EKF, bring my EKI to the other side, and it becomes a negative. That's good, that's what we want. And that must be equal to what's left over here, WM minus WF. So this is my change in kinetic energy. Simply depends upon the comparison of the motor's work to the friction's work. You see that? So if those two are equal, is there any change in kinetic energy? No, my robot goes at constant velocity. If I'm putting in more work than friction is taking out, what happens to my kinetic energy? It increases. And so I'm going to have more velocity. I'm speeding up because I'm doing more work, motors are doing more work than friction is taking out. And by the same token, then, if the motors are not doing as much work, then the kinetic energy is going to change. My change in kinetic energy is going to be negative, right? If the work done by friction is less than the work done by the motor, then my change is going to be negative. And so I'm going to have less kinetic energy, and therefore the robot's going to slow down. It's moving at a slower velocity. Okay, so let's take this situation then, and let's look in the next problem here in microtest 6. So suppose the robot turns off its motor. So this is going to be 0, right? If that's true, then what's left? Well, that's pretty straightforward, right? My change in kinetic energy now is simply equal to the work lost to friction, right? And we've got it negative here because I've gotten rid of my two sides, if you see that. And so a negative work means work is leaving the system. Makes sense. The other way you could think about it is that this change here is negative. Does that make sense? So whichever is the easiest way for you to think of it, it's perfectly fine. You do you. Okay. All right, so this all makes sense from an energy perspective. Those forces then are, let's draw our robot again. So here's our robot, and then the motor is providing this force. It's trying to change the momentum. It's trying to increase its velocity, which is going to increase its kinetic energy. Friction, on the other hand, is acting in the other direction. There's my velocity. And it's trying to take energy out. That force is trying to change the momentum by decreasing the momentum because it's in the negative direction, right? My momentum for my robot here is in the positive direction, right? If we define this to be positive. So this is trying to make the momentum be less. It's trying to make the momentum go in the negative direction. And you think about how we did our vectors way back in the first week of class. We talked about with the case of acceleration. If I have a velocity here and I apply an acceleration in the opposite direction, what happens to my velocity? It's going to decrease. And if I keep applying it, well, then it might go actually backwards. In this case, in case you didn't know, the friction cannot make anything go backwards because the friction is actually velocity dependent from that, but that's something for another time. Okay, so those are the first two laws. So the first law just says that if I have a net force, then I will have a change in momentum. We now know that that force has a different definition though. If there is no change in momentum, then the total forces must equal 0. But then, so this is Newton's first law. Newton's second law actually provides the definition of the force. So it would have been better if we'd made this one the first law. And this says that the force is defined to be the change in momentum, the average force in this case, is the change in momentum in a certain amount of time, or the instantaneous force is dp dt, where that's also a vector. And you see that we have vectors on each side, so it's looking good. All right, so turn over to the next page in your book. And now let's look at Newton's third law. Now, you've probably been told for every action there's an equal and opposite reaction. What the heck does that mean? Action is not defined, reaction is not defined. It doesn't really tell you much of anything, and Newton never said that. Newton never said that at all. So what he said was this. This was an aspect of forces. He said forces always come in pairs that are equal in magnitude but opposite in direction. Now that may seem weird, but really all Newton's third law is a statement of conservation of momentum. Let's say that, for example, look at microtest 7, I'm leaning against a wall. So here's my wall, right? And here's me with my beak nose, and I'm leaning against it with my extra long arms, right? So is my momentum changing if I'm just sitting there leaning against it? I'm not moving, right? So I've still got a momentum of 0. So no. Therefore, think about Newton's first law. If my momentum is not changing, am I experiencing a net force? No. Now, am I applying a force to the wall? Oh, you bet, right? I'm leaning against it. I'm totally leaning against it. So I'm applying a force in this direction. But we know this will be the force of Dr. K. We know that the force, though, the total momentum, is 0. Therefore, the net force must be 0. So that wall must be providing a force in this direction. And you see that's true? So the wall is actually pushing back on you. Now, if I want this net force to be 0, what can you say about the magnitudes of the Dr. K force and the wall force? They better be the same, right? If the magnitudes aren't the same, then they're not going to exactly cancel out. What can you say about the direction? Well, the direction is going to be opposite, right? Okay. So, before we get to this last one, let's make sure what we're talking about here. Conservation of momentum here, if it's 0, it had better stay 0. So I cannot have my momentum change. And so that means then that the sum of my forces must also equal 0. And that's what led to the idea of, well, let's write down my individual forces here. Let's say that we've defined this way to be positive, then positive, and this now is the magnitude of the force provided by Dr. K, and the negative, so plus a negative of the force provided by the wall, and again, this is a magnitude because my direction is right here, must equal 0, and so that tells me that my magnitudes must be the same. But it's going to be, if I look at the direction of the vectors, the only way that I can get this condition to be satisfied, or equivalently this condition, is if they're in opposite directions. So that's where the equal and opposite part comes from. And that's all that the third law is saying. Okay, so let's look at this last one. Anytime a robot has a change in momentum, it's either experienced a change in mass, right, or a change in velocity. Sometimes, but not always, the mass is going to be constant. And if you think about, if I've got a rocket engine, certainly the mass is not constant. I'm throwing mass out the back, right? So my mass is definitely not constant in that place. If you crash your car and a piece goes falling off, then your mass is not constant. In fact, in most situations, actually, your mass is not going to be constant. And so that is a very special situation of when the mass is constant. But let's suppose for the moment that we are in that special situation, all right? So if that happens, then let's say I have just a change in velocity, all right? So my momentum change is due solely to a change in velocity. So what do we call that change in velocity? What's the physical quantity that represents a change in velocity? That's the acceleration, remember? Okay. So I'm going to take microtask 8 and I'm going to put it up here so I've got some room to work. So let's stay with that special case. We're going to stay with that special case that says that the mass is constant. And even though we know that's almost never true, we're going to take that one special case. All right, so let's start with the definition of force, which is Newton's second law. And we're going to look at the instantaneous force for this one. Okay, well, this is Newton's second law, just copied straight down. If a force is defined to be the change in momentum in a certain amount of time. Well, okay, we can put in the definition for the momentum. That's mv, which is also a vector. So far, so good. If the mass changes in time, as it usually will, I can't pull that mass outside, can I? I can't pull that outside my derivative. But for the very special case where mass is constant, I can do that. And so I get m times dv dt. Well, what is dv dt? That's the instantaneous acceleration. And that is probably what you were taught in school, was Newton's second law. And yeah, it is, for the one special case where the mass is constant. If in the real world, it's almost never going to be true, right? It's very rare for you to have a case where the mass isn't changing. Something's happening. Even if your car has collided, you've burned some gas as you've been coming in, as you were approaching the wall there. So there's almost always a change in mass. But for this special case where I can use this F equals ma. Now, many times we can say that the change in mass is very small. And if we do that, then we can use this, but we need to make sure that we understand it's an approximation. It is not a law. It is very definitely not a law. It's just an approximation, and it's only as good as our approximation that this mass is constant, because that's what I had to do to pull this out. This equation, Newton's actual second law, applies in all cases. We can even use it with a rocket, because now my momentum change is not only due to the velocity change, it's also due to the mass change from that. And if we really wanted to get into it, we could derive the rocket equation that tells you, the force of the rocket engine. All right. Okay, so let's take a look at the... Okay, so now we need to get some units for this quantity of force. Remember, anytime we define a new physical quantity, we always have to have units for it. And we need some way to get that, so all we need is an equation. We can do it with dimensional analysis. So any equation will work. I could do this one, which is the actual original definition. Or, even though this only applies in a special case, this is in fact a force. It's going to have the same units as this one here. It has to, even though it only applies in that special case. So you could do either one. Probably this one's easier for obvious reasons. So this is, the kilograms is the mass, and then meters per second squared. So that is the fundamental units of my force. Let's make sure that we get the same thing up here when we do that. So this is going to be dmv, right, over dt. And so this gives me kilograms times meters per second, and then times another second in the bottom here. And so that's kilogram meters per second squared. So they give the same thing. The SI unit, this is the fundamental units. The System International unit for force is called the Newton, because the whole concept was from Isaac Newton. Newton actually invented the concept of a force. And the abbreviation we use for that is a capital N for that. Just to give you some idea of what this is. This is a force, remember. So one classic example of a force is the force of gravity. This is what's pulling you down. How do you measure your weight? Your weight is literally the force due to gravity. What units do you use for that? Well, you probably use pounds, right? Pounds are the unit of force in the English system. It's not a unit of mass. Just as a trivia question, do you know what the unit of mass is? In the English units, the unit of mass is a slug. I kid you not. And in engineering, unfortunately, in the United States, a lot of what you're going to do is going to be in the English system, just because that's what your instrumentation is in. All your machines are in the English system. And so you'll talk about a pound, you'll talk about a slug, you'll talk about a foot, things like that. Almost everywhere else in the world, though, you're going to be using System International. So we know that Newton is the unit of weight because it is a force. It's the force due to gravity, right? So this would be your weight. And just as an aside, we know that this is your mass and this is in kilograms, right? So the unit of mass in the SI system is kilograms. The unit of force, or weight, is the Newton. And to give you an idea, one Newton is about 1/4 of a pound, somewhere in there. So if you want to find out what your weight in newtons is, just take your weight in pounds and multiply by 4. And that will be your final answer for that. So now that we've introduced the concept of a force, we're going to be using this in quite a few situations from on out. Now, in many classes, they start with forces. They consider forces to be, kind of the most fundamental thing. It's a push or a pull, they say. But in reality, forces come from momentum. And you really have to talk about momentum before you can talk about forces, unless you want to kind of make up something that Newton said that he never actually said from that. So in the future, when you think about momentum, remember that momentum change is going to mean there's a force present somewhere. Now, the amount of force is not only going to depend upon the momentum change, it's also going to depend upon how fast that change takes place. So there's always two aspects to it. There's always that time aspect. This always also comes into play if you think about if we have constant mass, then we can say F equals ma, as you may have heard before. So if I have constant mass and there's a force, I also know there's an acceleration. Well, that makes sense, right? An acceleration is just a change in velocity, which is a change in momentum. Keep that in mind, and we'll work with that for the next few weeks. We'll see you next time.